The glitch in reality, why time keeps breaking. The interference pattern was already on the screen when Elena pressed the final toggle. Then the counts shifted clean, sudden, as if the past had been edited mid-sentence. She froze. Run it again. They did. Same flip. The choice they made after detection rewrote what had seemed decided. If causality bends here, what else does it take with it? Free will, memory, common sense. We're following the trail, from Bell tests that killed local realism, to devices where A before B becomes neither before nor after, to experiments that seem to entangle histories. Keep an ear out for a small calibration detail from 2018. It'll matter later. The moment everything bent backwards. It started on a Wednesday night, long after the cafeteria had closed. Elena's team had rebuilt a delayed choice interferometer, Wheeler's dare made real with fast modulators and patient grad students. The path length was locked. The detectors were calibrated. Off to the side sat the key, an electro-optic modulator that would, on a randomly chosen whim late in the run, either open the witch path door or close it to let interference through. Their rule was simple: detect the photon first, then flip the modulator. The pattern, by common sense, should be immune. It was. Stakes first because you should feel them. If outcomes depend on later choices, then the neat order we live by, cause then effect, starts to feel negotiable. You can still make breakfast and catch the train, but in the basement of the universe, the rails don't run one way. And if the rails don't run one way, what exactly are we choosing when we choose? Now the action. Wheeler's delayed choice thought experiment was a dare to the cosmos. Take a single photon into a mock Zander interferometer. If you keep both arms and recombine them, you get interference. The photon behaves like a wave. If you sneak in a device that marks which arm it took, the interference vanishes. The photon behaves like a particle. Wheeler's twist was to decide the setup after the photon had already entered. Dare the world to commit to wave or particle before you ask the question. Technicians a generation later turned the dare into hardware. With fast random number generators and modulators switching in nanoseconds, they chose the measurement late. Even later, some groups sent an entangled partner down a longer path, so the choice, basis on that partner, happened after the signal photon hit a detector, and they sorted the data in coincidence afterward. In Elena's lab, the late wasn't theatrical, it was engineered. Detection events were time-stamped. A separate controller driven by a random bit toggled the modulator after those stamps. Then they binned the counts. A wave context yielded fringes, a particle context gave a flat distribution. The unsettling part, the wave versus particle look seemed to depend on a choice made after the photon hit a detector. Colleagues joked, the photon knew. Elena waved that off. It didn't know anything. Our story about time did. Here's what actually happened, stripped of slogans. The apparatus produced entangled correlations between the traveling photon and an ancilla that carried the late choice. No signal ran backwards, no message to the past. The correlations were revealed only when you sorted detections by the delayed settings, a pattern in the joint data, not a causal rewrite of isolated events. That's the technical truth. But it doesn't rescue naive causality. Because the only way to make sense of the joint pattern is to give up a simple, forward-only narrative for individual outcomes. You can keep no signaling. You can't keep the idea that each detection had a context-free, pre-written character independent of the measurement you later pair it with. Meanwhile, something else was happening on the whiteboard. One student drew the timelines and realized there wasn't a single, clean time order shared by all parts of the setup. Detector clicks, controller toggles, coincidence sorting, their earlier and later belonged to different reference frames within the apparatus logic. That was the moment everything changed for the team. They stopped asking whether the photon switched its mind and started asking what counts as a cause when results live in correlations. Impact because the ripples spread far. Framing it as the photon knew invites a trap. You picture little billiard balls with tiny diaries. The better framing is blunt. You don't get to attribute definite properties to the system independent of the measurement context, including context set by later processing. That's not a press-release punchline. It's a working constraint. It kills the kind of causality that assumes a single, global order of explanation for every event. It preserves the causality that matters for signals and control. You still can't send a message to your past self, but it asks you to accept that explanation itself is conditional. Here's a micro story that stuck. Around 2 a.m., a postdoc named Fayez noticed a tiny drift in the timing electronics. Not enough to fake a retro flip, but enough to nag him. He pulled the box, resoldered a joint, and tightened the window that defined after. The flip stayed. He swore, then laughed, then wrote in the log, "Past remains susceptible to future definitions." The words were wrong in a strict sense. Definitions don't reach back, but the emotion, dead on. When your final choice determines how you slice the data, it feels like you're tugging on earlier moments. What nobody knew at the time was how central this feeling would become across the field. As teams refined Wheeler's ideas into quantum erasers and entangled histories, they found new ways to showcase that tug without granting it the power to signal. And as theorists built process-level descriptions, where you don't assume a fixed order in the first place, that tug stopped being a glitch and started looking like a feature. To understand why any of this holds force, why we're not just playing with language, we have to go back to the rulebook Bell made testable. He took the quiet assumptions behind the photon new and the world is sane and put them on the stand. Local realism wasn't a slogan. It was a pair of promises. Properties exist before you look, and nothing you do here affects what happens there faster than light. Those promises felt obvious. They didn't survive contact with experiments. Bell's shot at local realism. The Wednesday night feeling in Elena's lab of explanation slipping didn't start there. It traces to a quiet office in 1964, where John Bell sat with pencil and paper and asked a blunt question. Can a universe with local causes and pre-existing properties reproduce quantum predictions? Two pillars framed that question. Realism. Measurement outcomes reflect definite properties that exist before you look. Locality. What you choose or do here can't instantly influence what happens far away. Those pillars felt like common sense. Bell's move was to stop debating them and make them testable. To see why that mattered, we need the setup. Einstein, Podolsky, and Rosen had argued in 1935 that quantum mechanics must be incomplete because you could predict a distant outcome by measuring a partner here. To Einstein, that meant there were hidden variables, unseen details, that fixed results locally, no spooky action required. Bell took that hope seriously and did the math. He derived an inequality, a bound on how strongly distant outcomes could correlate if hidden variables determined them, and if influences respected light speed limits. Quantum theory predicted correlations that could exceed that bound. Stakes before we roll film. If experiments violate Bell's inequality under clean conditions, then any worldview that keeps both locality and realism is out. You can try to dodge with loopholes. Maybe detectors miss a tricky subset, maybe settings aren't free enough, maybe a subliminal whisper leaks through wiring. But each dodge is a bill to pay. Close the loopholes and you're asking the universe directly. Action spread across decades. Early tests in the 1970s and 1980s hinted at violations but left room for doubt. Low detector efficiencies, slow setting switches, short distances. Step by step, labs tightened the screws. Polarization entanglement got cleaner. Electro-optic modulators flipped settings in nanoseconds. Stations moved kilometers apart. By the mid-2010s, multiple groups reported loophole-free violations. In 2015, a team in Delft entangled solid-state spins and swapped entanglement across 1.3 kilometers, spacing events so that any influence would have had to outrun light. Also in 2015, photonics teams in Boulder, NIST, and Vienna used superconducting nanowire detectors and fast random number generators with high detection efficiencies to close fair sampling arguments under space-like separation. NIST's violation cleared the classical bound by double-digit sigma after conservative bias accounting. When the statistics landed, the quantum predictions held, and local realism did not. Meanwhile, something else sharpened: definitions. Bell's local causality isn't just no faster than light messages. It's a precise constraint on joint probabilities. Once you condition on all causes in the past light cone, distant outcomes shouldn't share unexplained correlations. Realism, in this context, means that outcomes are functions of underlying variables that don't depend on which other measurements you perform. Add measurement independence, the assumption that your choice of settings is statistically uncorrelated with those hidden variables. Taken together, those assumptions define the inequalities limit. Break the limit, and at least one of them must go. Human moments kept the math honest. In one seminar, a young researcher proposed saving realism by letting the hidden variables depend on the measurement settings. A senior colleague asked, "So the settings we choose are already encoded in the variables we're testing?" The room went quiet. You can take that path, superdeterminism, but the universe you get is pre-wired so tightly that free choice becomes theater. Not impossible, just costly. Impact landed with engineering receipts. Loophole-free tests counted every trial, pre-registered analyses, audited timing, and bounded any predictability in random sources. Some used cosmic photons from distant quasars to choose settings, pushing any hypothetical conspiracy back billions of years. Others crowdsourced bits from human clicks to diversify entropy sources. The Big Bell test, 2016, enlisted more than 100,000 participants worldwide in a one-day push to generate setting bits for multiple labs. Even after accounting for small biases, the chance that a local realist model faked the data dropped to vanishing levels. The verdict was signals outrun light. It was you can't keep locality and context-free realism together. Here's the twist that loops back to Elena's night. Bell doesn't force you to accept backward messages or instant telepathy. He forces you to abandon at least one comfortable idea. Many physicists keep operational no signaling, no messages faster than light, and drop the notion that outcomes have pre-existing, context-independent values. Others keep realism but accept non-local explanations, like pilot wave theories with influences that aren't confined by light cones in the underlying picture. Either way, the single, global script of causes gets shredded. A micro-story fixed the feeling. During a late shift, a student plotted correlation curves live as settings flipped. Each new point nudged the Bell parameter past the classical bound. She stared, then whispered, "So the world really does this." Not rhetoric counts on a screen, latencies audited, spacetime diagrams taped to the rack. What nobody knew at the time was how the language would change once those diagrams became standard. Locality loophole stopped being a press release phrase and became cable lengths, fiber delays, and clock sync budgets. Freedom of choice became entropy rates and device unpredictability bounds. The romance faded, the constraints hardened. In the aftermath, Bell's theorem became the field's spine. It disciplined stories about delayed choice and quantum erasers. If a late slice seems to sculpt earlier outcomes, check whether you're smuggling realism back in. Pretending detections carry meanings independent of the joint context. Bell showed where common sense breaks. The next wave would test a deeper habit, that there even is a single before and after to hang explanations on. The loopholes slammed shut. While the theory tightened the screws, the defense had three places left to hide: bad detectors, leaky locality, and the uneasy suspicion that the random choices weren't truly free. Stakes were simple. Leave anyone open and a clever local realist can wriggle through. Close all three at once and you're not arguing with metaphors anymore. You're asking nature point blank. No excuses, Elena told the team. Just counts and cones. Action as it moved from whiteboards to racks. In Delft, a team used nitrogen vacancy centers in diamond, solid-state electron spins that could be entangled and then separated by about 1.3 kilometers. They performed entanglement swapping and chose settings fast, so that each side's measurement and choice were space-like separated. The runs were few but clean. Every trial counted, no fair sampling assumption, and a Bell parameter that cleared the classical limit with room to spare. Meanwhile, photonics labs in Boulder and Vienna took a different route. They built bright polarization entangled sources and paired them with superconducting nanowire single photon detectors, whose efficiencies finally crossed the painful threshold where maybe you just missed the unfriendly events stopped being plausible, enabling statistically strong violations, e.g., multi-sigma, without fair sampling assumptions. Electro-optic modulators flipped measurement bases in nanoseconds. Random number generators spit out bits at high rates with bounded predictability. Stations were separated by hundreds of meters to kilometers, cable delays measured, fiber length stabilized, and every click time stamped to the nanosecond. They didn't just claim space-like separation, they drew the light cones and published the latency tables. Stakes sharpened around randomness. Freedom of choice isn't a mood, it's min entropy per bit and timing budgets. Some teams sourced randomness from fast physical devices, audited for bias, and folded worst-case predictability into their hypothesis tests. Others pushed further. In one series, cosmic photons from distant quasars set the switches, so any hidden coordination would have needed roots billions of years old. In another, the Big Bell test, 2016, enlisted more than 100,000 people worldwide in a one-day push to generate setting bits for multiple labs, an explicit attempt to address freedom of choice, concerns by diversifying entropy sources. Human moments kept it from becoming a cartoon of perfection. In one late run, a graduate student, Anna, found a 3-meter mismatch in fiber lengths between stations. She caught it at dawn by watching phase drift when the building HVAC cycled. The fix was a coil of fiber on foam, labeled thermal, do not touch. That coil turned a fuzzy spacetime diagram into a clean one. Days later, the violation reappeared exactly where the inequality said it shouldn't. Meanwhile, something else was happening in the statistics. The field adopted analysis discipline that would have made a skeptic smile. No cherry picking. Every attempt counted, successes and misses. Pre-registered analysis pipelines. Explicit p-value calculations that included worst-case biases in the random sources. Adversarial tests where timing skew was deliberately injected to confirm the violation vanished on cue. When the numbers landed, 2015, and after, the chance that a local realist model produced the data fell to vanishing levels. Clarify what actually closed. The detection loophole, high-efficiency detectors and careful accounting so you don't assume the sample you measured represents the whole. The locality loophole, space-like separation between each side's setting choice and the other side's outcome, with device latencies verified, so no subliminal nudge can sneak through. Freedom of choice, demonstrated independence between settings and any variables that might influence the outcomes, bounded by entropy estimates or driven by sources outside the lab's past light cone. None of these moves smuggle superluminal messages into the story. They just corner local realism until it runs out of room. Micro-story from a control rack. Fayez noticed a weak correlation between an RNG's temperature and its output bias, still within spec, but enough to make him sweat. His hand shook a little when he pulled the module, missing a bias like that is how careers get dented. They halted, replaced a jammed fan, recharacterized min-entropy, and reran with the bias folded into the hypothesis test. The violation shrank a hair and got more convincing. In the log he wrote, less pretty, more true. Impact wasn't a single trumpet blast. It was a stack of receipts. Delft's solid-state test shut the door on detection and locality with matter qubits. Boulder, Vienna, and others did the same with photons, high rates, and unforgiving counting. Cosmic source test shoved any hypothetical conspiracy into the deep past. The message was boring in the best way. Under conditions designed by skeptics, quantum correlations violate Bell's inequality. If you insist on saving both locality and context-free realism, You're left paying with superdeterminism, a universe where your setting choices are baked into the same variables that decide the outcomes. Not logically impossible, just a bill most aren't willing to pay. Meanwhile, the culture shifted. Papers started printing spacetime diagrams alongside correlation plots. Latency budgets sat next to visibilities. Randomness extractors got footnotes with min-entropy bounds. Labs ran blind analyses, separating exploration from confirmation. What used to be a headline, loophole-free, became a checklist. Distances, delays, efficiencies, entropy rates, jitter tables. Here's the moment that fed back into Elena's lab. With Locality's explanatory shelter gone, the team stopped reaching for hidden signals and started watching how context defines meaning. No faster than light messages. No retro phone calls. Just a hard limit. You can't tell a single, global, context-free story about outcomes. That limit didn't just kill a worldview. It shaped the next question. If space can't salvage a classical script, maybe time won't either. And that's where the field turned, to processes where a before B and B before A aren't the only options, and order itself becomes a knob. Quantum switches, an indefinite causal order. While the Bell world was draining its loopholes, another corner of the field asked a rude question. What if the order of operations isn't a given at all? Not A before B, not B before A, but both held together coherently so neither story wins. The device that made that question real has a blunt name, the quantum switch. Stakes are obvious if you stare at a timeline. If first and second can superpose, then the arrow you lean on to explain cause and effect stops being a fixed backdrop. It becomes a resource you can wire. Here's the action without slogans. In a normal circuit, you pick an order. Apply operation A, then operation B, or swap them. Either way, there's a list. The quantum switch adds a control qubit that routes the target through a right arrow B when the control is one way and B right arrow A when it's the other. Prepare the control in a sewer position, and the target sees both orders at once. Recombine the paths, and interference appears between A then B and B then A. If that interference can't be explained as a mixture of definite orders, you've built a process with indefinite causal order. The math calls it causally non-separable. It isn't that time runs backward. It's that before and after aren't globally meaningful for those operations. Meanwhile, theorists built the book to certify this. Orshkov, Costa, and Bruckner wrote the process matrix framework. Instead of assuming a causal scaffold, describe what correlations are allowed when each lab is locally quantum and globally agnostic about order. Within that set, some processes admit a decomposition into Alice before Bob or Bob before Alice, possibly mixed. Others don't. For those, you can design a causal witness, an observable whose value can't cross a bound if a fixed order existed. Cross it, and order wasn't just unknown, it was undefined. Now the bench. Photonic teams encoded the control in polarization, and the target in a spatial mode or another photonic degree of freedom. Beam splitters and interferometers routed the photon so that its polarization coherently chose which operation it hit first. Optical elements implemented A and B as gates on the target. Recombine, measure the control in the right basis, and read off the interference. When they evaluated a causal witness tailored to their setup, the numbers landed in the non-separable region. Trapped ion and NMR variants did the same trick with different hardware. The common thread was verified coherence across the two orders, and audits that ruled out hidden asymmetries pretending to be fixed order. Photonic platforms remain the leading demonstrations, with ongoing refinements reported into the 2020s. Stakes in the practical sense. Does this buy anything? Yes, in places where the order you choose matters for how noise stacks up. Suppose you're asked whether two black box channels commute. With a fixed order, you need multiple queries and still accept errors. With a switch, the commutator is encoded directly in the interference term, letting you detect non-commutativity with fewer calls than any definite order routine. That's a clean query complexity win. Communication complexity offers another lever. In certain tasks where Alice and Bob must compute a function of their inputs with minimal communication, a switch can shave a bit. Fewer classical messages for the same success probability. Not a miracle cure, a line item that persists under drift if you keep coherence. Clarify what this is. You can't smuggle a message to your past self by hiding it in the order. No signaling remains intact. Try to extract a classical which came first, bit mid-process, and the interference collapses, along with the advantage. The resource is the superposition of orders itself. Treat it like a classical wire and it evaporates. It only pays if you don't peak, Elena reminded the room, and for once nobody joked. Too many late nights had taught them how a single peak can turn a month of data into noise. A micro story from the lab floor. Alignment sagged after midnight. Marta shimmed a mirror with a folded business card. The fringes stabilized, their causal witness jumped from barely significant to clean. She scribbled, "Order certified by 80 microns of paper." The joke held more than humor. In these devices, tiny asymmetries fake fixed order. The shim didn't add magic. It removed bias so the non-separability could show. "Keep the path honest," Elena said. "The story gets honest too." Meanwhile, certification itself matured. Beyond witness values, groups worked toward device-independent or semi-device-independent protocols. Logic that, under the assumption of no superluminal influence, can certify indefinite order without trusting the inner workings of the devices. These routes are emerging and still being refined in current research, with notable progress reported through the early to mid-2020s. Others mapped how far switches outrun fixed circuits in query complexity, proving separations that no clever definite order circuit can close without a blow-up in calls. That matters because it moves the claim from neat optics to provable resource, while ongoing experiments work to match those separations in practice. Impact hooked back into Elena's reframing. If you can certify a process that refuses any single causal order, then cause precedes effect, becomes local and contextual, true for many macroscopic stories, but not a law you can force on every quantum task. The lab stopped drawing single arrows over their diagrams and started drawing boxes labeled process, then checking which interventions fit inside a consistent causal account. Sometimes both A before B and B before A are valid descriptions mixed over runs. Sometimes neither alone will do, only their coherent superposition matches the data. A human beat sealed the shift. After a seminar, Anna's father asked, "So sometimes there isn't a first," Elena said. "For those operations, first isn't a property you can assign without breaking the device." He frowned. "Then how do you assign blame?" Laughter, then Marta. "We don't. We assign design." The rule the team taped above the bench was simple. Order is a knob. Spend it where it pays. Fewer queries, tighter bounds, lower messages, and protect it like you protect entanglement. Try to turn it into a headline about time travel and you'll lose it. Entangled Histories and the Quantum Eraser Revisited. 3 days after the business card shim fixed the switch, the team turned the table into a storyteller. They rebuilt delayed choice as a quantum eraser, tagging which path information with an entangled partner, then deciding at the end whether to keep or erase that tag. Stakes were blunt. If a late choice can recover interference after the signal's already been recorded, what becomes of the past that looked like it had been settled? Action first. They split each photon at the first beam splitter. The signal took the short route to a screen. The idler got a long fiber delay, which path marks road on polarization. Upper arm tagged horizontal, lower arm vertical. That marking killed interference in the signal's raw counts because path information and fringes refused to cohabit. The twist sat on the idler station. Measure in the HV basis, and when you sort coincidences, the signal sub-ensembles stay flat, particle-like. Rotate to the diagonal basis, and sorting by the idler's outcomes reveals 2 clean, phase-shifted interference patterns, wave-like. No magic appeared on the wall. The fringes lived in correlations you could choose to reveal late. Meanwhile, the tug pulled at nerves. The idler's delay put the basis choice after the signal's time stamp. That timing made the reveal feel like a retro edit. It's as if the screen had fringes all along and we turned them on afterward, a student said. Elena shook her head. Not turned on, exposed by the cut we chose. The room felt it, the mix of relief and discomfort when a paradox turns into a rule you can use. The room went quiet. The distinction mattered. No signal to the past. No rewrite of logged clicks. Just a late decision about which joint slices count as a pattern. Here's the structure that kept them honest. The eraser works in coincidence. Once path marking exists, the signal alone carries no interference you can access locally. Only by conditioning on the idler's outcome in a complementary basis do you carve sub-ensembles where the signal's distribution shows fringes. That conditioning defines the effective measurement you performed on the joint state. Change the slice, change the story, without touching the past. A micro story made it visceral. Fayez exported the run's time tags and tried slicing the signal with a random bitstring unrelated to the idler. The plot stayed flat. Then he replaced the random bits with the idler's diagonal basis outcomes. 2 clean fringes bloomed, offset by half a period. Same signal clicks, different partition. He scribbled, "Interference is a relationship, not a property." Elena underlined it. Relationships can be revealed late without being sent back. Meanwhile, a quiet lever turned under the hood, the coincidence window. Back in 2018, they'd set W to 2.5 nanoseconds because detector jitter sat around 450 picoseconds and fiber drift stayed under a nanosecond. This time they scanned W too wide, and mismatched pairs washed out visibility. Too narrow, and genuine pairs got chopped, biasing the sub-ensemble. There was a sweet spot that matched the measured joint arrival distribution. When Anna slid W by 200 picoseconds in software, the fringe phase shifted by exactly the amount their model predicted. She laughed. Phase by slice, not by signal. Her father, peering at the printout, said, "Like shifting the chorus against the drums." She nodded. "Same tracks, new groove." Then she went quiet and said, "I hate that a tiny software knob decides whether there's a story at all." Elena answered, "It decides which story is honest." Stakes sharpened around meaning. If the pattern you care about depends on post-selection and windowing, then your slice isn't cosmetic. It's part of the instrument. That doesn't make the effect fake. It makes it conditional the way Bell taught them to expect. Try to tell a context-free story. The photon had wave-ness at detection, and you'll trip over the statistics. Tell a context-full one. The joint measurement reveals fringes in a subspace defined by a later basis, and the numbers line up. Meanwhile, theorists pushed language that fit what the bench showed. Pre- and post-selection frame a process with boundary conditions at both ends. Between them, weak measurements can map weak values, quantities that depend on both anchors without enabling signals. In that time symmetric bookkeeping, the eraser stops looking like a paradox. It's a constraint story. The allowed middle correlates with the ends. The feeling of a retro tug is the human side effect of consulting future data to choose a slice. A second micro story sealed the tone. Marta plotted unsorted signal counts next to the sorted fringes on the same axes. Anna's father asked, "So which is real?" Marta said, "Both. One is the whole file, one is the answer to a specific question." He frowned, then smiled. "Like a trial, same evidence, different charge." Elena added, "And the verdict only exists once you decide which charge." Impact reached beyond pedagogy. Sensors can exploit correlations across time by conditioning late to boost signal to noise. Protocol designers learned to treat post-selection devices as first-class instruments, not afterthoughts. Language gets policed. No signaling survives. Causality as explanation becomes conditional. The arrow you live by, records, redundancy, and heat stays intact. The arrow in the lab, coherence, conditioning, and slices, bends. And for viewers, that's the hook. You don't need time travel to feel the floor tilt. Just a question asked precisely enough, late enough, to make a new pattern appear. Clarify the headline you shouldn't write. The past didn't change. The wall's raw counts stayed the wall's raw counts. The later choice changed how you partitioned them, which joint amplitudes you let interfere, and which sub-ensembles you plotted. That's not pedantry. It's the operational boundary that keeps paradoxes out and advantages in. And at the edge of the whiteboard, a note in thick marker: freedom isn't free. In Bell tests, free settings are guarded with space-like separations and cosmic photons. In erasers, free slices are guarded with calibrated windows and honest models. Either way, the world charges you for context. Pay it, and the weirdness pays you back. Time-symmetric physics versus our one-way lives. To make sense of why the eraser's late slice doesn't break physics, Elena pulled the team back to first principles. Most microscopic laws do care which way time runs. Schrödinger's equation is symmetric under reversal when you flip complex phases appropriately. Maxwell's equations are too. Strictly, certain processes violate T individually but respect CPT. Here we mean the practical reversibility of the dynamical equations used in these experiments. On paper, you can run the movie backward and the rules still hold. So why do kitchens and cities feel like one-way streets, while glass tables let time flex? Start with a bookend view. Aharonov and colleagues sharpen a time-symmetric formalism where you don't just prepare a past state and push it forward. You also condition on a future outcome and let a second state run backward. The core ideas date back decades and continue to be developed in contemporary work. Between those anchors, gentle probes, weak measurements, pick up weak values that depend on both ends. It sounds retrocausal because the future appears in the middle. It isn't messaging, it's constraint. You're narrowing the set of middle histories to those consistent with both boundary conditions. The past didn't change. The middle was never an isolated fact. Meanwhile, human life hides this symmetry behind records and heat. Decoherence takes fragile phase relations and splashes them into the environment. Air molecules, stray photons, bench vibrations, so thoroughly you can't pull them back. That sprawl writes redundant copies. Thermodynamics adds the shove. Given the universe's low entropy beginning, typical evolutions go from fewer microstates to more. We remember yesterday because there are many traces. We don't remember tomorrow because it isn't redundantly etched yet. The one-way feeling is the weight of records, not a law the equations demand. Stakes on Elena's bench. A delayed choice eraser can consult a future basis to reveal a structure in joint data without letting you phone yesterday. Time-symmetric language absorbs that cleanly. You prepared entanglement at the start, post-selected an idler outcome at the end, and the allowed correlations in the middle reflect both. The coincidence window and post-selection don't edit earlier clicks. They define the effective measurement you realized across time. If you try to yank a pattern out locally, ignoring the final anchor, it isn't there to take. Action with a desk drawer thought that the team argued through at 2 a.m. the three-box paradox. Pre-select a state spread across 3 boxes, post-select a different superposition, and weakly peek in between. You infer, as if, the particle sits with weight 1 in 2 boxes and -1 in the third, numbers that offend classical stories. The fix is the same as in the lab. Weak values are relational signals determined by both bookends. They don't announce hidden certainties. They report how an intermediate probe couples under 2 constraints. Meanwhile, operational guardrails hold. No signaling keeps earlier marginals immune to later choices. You can condition later to sort subsets that show interference, but you can't change what a local observer already recorded without access to the joint slice. That's why quantum cryptography still works, why device-independent protocols survived the loophole closing era, and why nobody in Elena's group confused constraint with control. A human beat kept the math from floating away. Anna's father stared at the screen and asked, "Are you saying tomorrow decides today?" Anna said, "No. I'm saying when we tell the story of today, we're allowed to include what tomorrow turned out to be if we're honest about what question we asked." He nodded. "Like tallying a game once the last inning ends." Elena added, "And the umpire doesn't call plays retroactively. The scoring rules were fixed." The thermodynamic arrow set the boundary for daily life. Decoherence makes superpositions fragile in kitchens, courts, and traffic. Environment's broadcast pointer states, quantum Darwinism's lesson. So many observers can sample the same facts without disturbing them. That redundancy is why we can agree on a mug's location without aligning interferometers. It's also why retro-field stories don't leak outside glass tables and cryostats. The environment chooses for us what survives. Meanwhile, time-symmetric accounts offered a trade some found cleaner than spooky explanations across space. Keep strict locality in your deeper story by letting ontic details depend on both preparation and later setting. Retrocausal models in the price, Wharton spirit. You relax measurement independence at the microscopic level but preserve operational freedom. Nobody can exploit the dependence to signal. It's a bill you either pay in time, constraints that run both ways, or in space, non-local influences and hidden dynamics. The experiments don't force which currency you choose, they force you to pay. Stakes for design were concrete. On the switch, coherence across orders lives or dies by isolation. Treat order as a resource the way you treat entanglement. On the eraser, coincidence windows and post-selection belong in the instrument model. Treat slices as part of the question, not an afterthought. On both, verify no signaling by auditing local marginals as you sweep late choices and timing. When those checks pass, the retro tug is just the feel of conditioning working as intended. A final micro-story pinned the lesson. Fayez wrote on the whiteboard, "Maps can be drawn after the trip," Marta added, "Road still there." Elena circled both and said, "Good. Next, let's see if causality itself admits bounds the way locality did, and whether we can step past them without breaking the guards." Causal inequalities and their violation. While Elena's team was getting comfortable speaking two languages of time, a hallway question wouldn't quit. If Bell gave us a bound for local realism, could there be a bound for causality itself? Not no faster than light, but no process that obeys a definite global order can win this game beyond a limit. Stakes were sharp. If you could write such a bound and then beat it with hardware, you'd pin cause first to the same board where local realism already hangs. Action started with a different playbook. Orshkov, Costa, and Bruckner introduced the process matrix framework. Describe what correlations Alice and Bob can produce when each lab is locally quantum. Inputs, outputs, controlled operations, without assuming a background timeline stitching them together. Follow-ups through the 2010s and early 2020s sharpened witnesses and tasks for certification. Within that space, some processes can be decomposed as Alice before Bob or Bob before Alice, or a mixture. Others can't. For those, you can craft a causal inequality, a limit on success in a carefully designed task that any fixed order must respect. Here's how one of those tasks feels from the bench. Alice and Bob each receive a random input bit. There's also a control bit C known to both. Their goal is conditional. If C equals 0, Alice should output Bob's input. If C equals 1, Bob should output Alice's input. In a world with a fixed order, someone always goes first. If Alice goes first, she can't know Bob's input in time when C equals 0. If Bob goes first, he can't know Alice's when C equals 1. Any definite order strategy caps the overall success probability below 1. There's a tight bound. Meanwhile, a quantum switch sneaks in a different resource. The order itself is coherently controlled. The control qubit prepares a superposition of Alice before Bob and Bob before Alice, and the target system carries the data the labs act on. Because the two orders interfere, a carefully chosen set of local operations lets interference terms carry just enough cross-information to push the success rate beyond the bound. No message goes backward. No side channel appears. The violation lives in interference between orders that no mixture of fixed orders can imitate. Definitions matured alongside the optics. A causal witness plays the same role here that CHSH plays for Bell, a tailored observable whose expectation can't exceed a threshold if the process is causally separable, i.e., decomposable into a mixture of definite orders. Design the witness for your device, measure it, and audit the result. Cross the threshold and you've certified causal non-separability. That language matters because it keeps the claim honest. You're not saying time broke. You're saying no single global order explains these statistics. Bench work got fussy. Photonic groups encoded the control in polarization and routed the target through two black box operations, A and B, implemented with phase shifters and wave plates inside compact interferometers. The photon's polarization coherently chose whether it hit a before B or B before A recombination, let the two histories interfere. Random inputs selected which local transformations Alice and Bob applied. At the end, detectors registered outcomes, and the lab computed a witness value. On good nights, the number landed outside the fixed-order region, beyond error bars that included drift and bias. A microstory captured the knife edge. 1 week, their witness hovered under the bound. Alignment checks passed. Marta swapped two identical phase plates between the A and B paths. The violation appeared. Her relief was audible. 2 weeks of doubt evaporated in a single clean number. She wrote, "Symmetry isn't optional. In this game, any hardware asymmetry leaks a preferred order that drags you back under the bound." The fix wasn't mysticism. It was engineering. Equalize loss, match phases, stabilize path lengths, and verify that flipping labels a left-right arrow B leaves the statistics unchanged. Meanwhile, skeptics pushed certification further. Instead of trusting device models, recent protocols moved toward device-independent guarantees, under the assumption that no superluminal signaling is possible between Alice and Bob's labs. Certain observed input-output statistics can only arise if the underlying process lacks a definite order. That's a heavy lift, but it mirrors the Arc-Bell tests followed, from trusting apparatus to bounding it. Results along these lines have appeared in the early to mid-2020s and continue to tighten. Clarify what was and wasn't violated. Causal inequalities assume that there exists a global, fixed order, even if you do know which one on a given run, and that the process you implement is a mixture over those orders. Violating the inequality shows that such a mixture can't reproduce your data. It does not show that effects cause causes, or that you can message the past. Local operations remain quantum. No signaling holds across space like cuts, and attempts to extract a classical which order. Bit-mid process collapse the very coherence that gives you an edge. Impact spread in 2 layers. First, certification. Labs could now stamp causally non-separable on a process with the same seriousness that they stamp entangled on a state. That's useful because order joins entanglement and coherence as a resource you can allocate and protect. Second, advantage. Query complexity results proved separations. There are tasks where a quantum switch needs fewer calls to black box channels than any fixed order circuit can manage without a blowup. Communication tasks saw bit-level savings. Metrology scenarios found noise regimes where indefinite order lifts precision by reshaping how errors combine. These advantages are task and noise model dependent and are an active area of current benchmarks. A human beat made the stakes legible. After Elena's talk, Anna's father asked, "So you beat a rule because you changed the rules?" Elena nodded. "We beat a bound that assumed a single order by using a process that doesn't have one." He squinted. "And you still can't call yesterday," Marta smiled. "Our phones obey like cones." He exhaled, half laughing, like a knot behind his sternum finally loosening. The lab taped a new rule beside order is a knob. The rule read, "Bounds reveal budgets." A causal inequality tells you the best you can do if you commit to a timeline. Violate it and you've found slack you can spend. Fewer queries, fewer bits, better precision. But spend it sloppily, peek at the order mid-flight, leak asymmetries, and the budget vanishes. This was the moment Elena circled a date on the wall calendar and wrote build mode. Bell had given them discipline. The eraser had taught them conditioning. The switch in causal games gave them a lever. Next, They turn that lever into devices that deliver edges quietly, under drift, with receipts. Building with broken order, quantum advantage from causal weirdness. While the witness graphs were still taped to the wall, someone down the hall asked the question that cuts through romance. Does any of this win a budget? Stakes were immediate. If indefinite order saves even a single black box call in a routine you have to pay for, the accountants care. If it trims a bit off communication when channels drift, network engineers care. If it squeezes more precision out of noisy probes, the metrology crowd cares. Order is a knob, only matters if turning it buys you something under stress. Action with a problem simple enough to price. You're handed two unknown channels, A and B, and asked whether they commute. In a fixed order world, you try a right arrow B, then B right arrow A, compare outputs and average over noise. You need multiple queries to beat chance. Elena's team coded the switch version. Prepare the control in a sewer position. Route the target through A and B in both orders coherently, then read out the interference term that encodes the commutator. On their photonic rig, it meant fewer total calls than the best definite order routine could manage at the same error rate. Not a cosmic leap, a clean, counted skip. When channels are rented or time is scarce, one fewer call is a line item you feel. Meanwhile, communication people showed up with a tight game. Alice has X, Bob has Y, and together they need F, X, Y with as little communication as possible. In the fixed order world, there's a proven lower bound. Someone must send at least one classical bit, with a switch mediating who effectively goes first. Elena's group implemented a protocol where interference carried cross-information, shaving that bit down under a matched noise model. Anna plotted success probability versus sent bits. Two curves hugged, then separated with the switch. She wrote, 1 bit back. It stuck because it was honest. Not 0 bits, not magic, just one fewer message to achieve the same guarantee. A micro story from a weekend test made the advantage feel industrial. Marta deployed their commuting test routine on a remote photonic platform. The provider exposed two noisy channels as services. A drifting phase flip. B, a depolarizer with hourly mood swings. She sent 2 jobs, fixed order and switched, same total budgeted calls. Monday morning, the provider's engineer wrote, switch beats our own benchmark under drift. Not by much. Enough to matter when drift is the enemy and budgets are capped. Meanwhile, metrology turned the knob differently. Suppose a parameter theta is imprinted by 2 noisy processes whose errors stack badly in a fixed order. Put the order in sewer position, and the cross term redistributes error so the quantum Fisher information rises under the same power and sample constraints. Elena's team built a toy version with controllable dephasing in A and phase encoding in B. The switch lifted precision in the worst regime, where fixed order underperformed because the wrong noise hit first. They didn't promise miracles. They published the noise model, the window where it paid, and the place it didn't. Clarify limits because hype eats trust. The switch doesn't accelerate clock time. It reduces queries bits or worst-case error under specific tasks and noise. Ask it for a classical who went first. Bit mid-process and the advantage collapses. Leak asymmetry and you effectively pick an order. The edge shrinks. Treat order like entanglement. Protect coherence, match loss, and don't poke it with the wrong meter. Meanwhile, theory kept handing them receipts. Query complexity proofs drew a line. For certain black box families, any definite order circuit needs exponentially more queries than a switch-based higher order process. Communication tasks got sharper separations. Even simulation results stacked in their favor. Trying to fake a switch with extra fixed order calls hit lower bounds that made the simulation impractical at modest sizes. You can emulate it. Stop being a serious objection when the emulation cost blew past the savings. A human beat grounded the pitch. Elena briefed a room of network engineers. One asked for the killer app. She said boring wins, fewer calls to unreliable boxes. Another asked about drift. Marta answered, we tested under hour scale drift. The edge shrank gracefully, then held. Engineers nodded. They live in the world of partial wins and failure budgets, not press releases. Ship the receipt, not the slogan, someone muttered, and Elena smiled. The lab shifted from proving to productizing. They added a new spec to their internal sheets: coherent order depth, the number of operations they could superpose in order before interference fell below a target. They built calibration routines that treated order like a qubit, randomized benchmarking for the switch path, symmetry checks under a left-right arrow B swaps, and sanity tests under no signaling assumptions that trended toward device independence as protocols improved. They wrapped the routines into a small library: toggle, fixed order; toggle, switched. The compilers chose when to spend the resource based on a cost model tied to drift and loss. A micro-story sealed the cultural change. Fayez printed a plot: error versus channel budget, fixed versus switch under a realistic loss model. The curves were neck and neck, then split by a steady margin exactly where the model predicted. He taped it above the bench with 3 words: order saves money. Under it, Elena wrote, when earned. Impact rippled in small, stubborn ways. A censored demo held spec through a week-long drift because a switch-based protocol reshaped how noise stacked. A cloud client hit a classification target with 1 fewer call per sample across a weekend of shaky stability. A network trial shaved a control bit off a bottleneck. None of it broke causality. None of it sent messages to yesterday. All of it turned a philosophical oddity into an engineering budget. And yet, as buses hummed and coffee cooled, another question kept needling. If order is a resource you can spend and certify, what happens when the stage, space, and time themselves aren't fixed goods but emergent ledgers of correlation? The lab could bill advantages, but the hunch tugged. Maybe cause itself is an accounting rule the world enforces with constraints, not a law we impose. That would send them back to an old log from 2018, to a tiny window that moved a fringe by 200 picoseconds, and to a principle they hadn't named yet. If spacetime emerges, what happens to time? While the witness plots were still blue taped to the wall, a whisper in the literature turned into a hallway argument. What if space and time aren't the stage, but the set pieces, props built from deeper correlations? Stakes were blunt. If geometry is bookkeeping for entanglement, then cause might be a contract that mostly holds, not bedrock. Locality becomes something the world earns from patterns, not a rule handed down. Action started with a bridge nobody expected. ER equals EPR. Maldacena and Suskind's conjecture that Einstein, Rosen bridges in gravity track Einstein, Podolsky, Rosen entanglement in quantum theory. Not a traversable wormhole you can text through, just a map. Connection in geometry mirrors connection in quantum state space. Meanwhile, tensor networks, those efficient webs for many body wave function, did more than compress numerics. Draw the right network and a curved space shows up. Swingle and others noticed that distance in the emergent geometry matches how strongly 2 parts are entangled. More entanglement, shorter effective distance. Less entanglement, farther apart. Meanwhile, gravity's favorite sandbox, add SCFT, kept throwing signals. The Ryu-Takayanagi formula tied a boundary region's entanglement entropy to the area of a minimal surface in the bulk. Tweak entanglement, reshape geometry. Push to small perturbations, and you recover linearized Einstein equations from entanglement constraints. The moral was hard to unsee. If you squint, gravity looks like how changing entanglement reads when you speak geometry. Stakes back on the bench. If locality is emergent from how correlations wire up, then light cones and diagrams are effective summaries that hold when the wiring is tidy. In messy regimes, high entanglement, coherent routing, locality can blur just enough to make Bell violations unsurprising and indefinite order feel natural. You aren't breaking relativity. You're noticing that its smooth fabric might be woven out of information. Elena's crew didn't swap optics for holography. They borrowed the picture. In their heads, the interferometer wasn't a table of mirrors. It was a miniature tensor network. Two paths that interfered weren't near because a ruler said so, they were near because the circuit stitched them to interfere. Tagging which path loosened that stitch, erasing, by conditioning on a late idler basis, reglued the connection in correlation space. No retro message. Just a different geometry of relationships, once both ends of the run were fixed. A micro story made it stick. Fayez drew two dots A and B far apart. He drew a thick line and wrote max int. Far in the room, he said, neighbors in code. Marta added a third dot C thinly linked to both. C's far from everyone, she said. Costs more bits to reach. Elena circled the line between A and B. This is why our explanations live in correlations. The map on the bench isn't the road the process takes. Clarify the boundary between bold and reckless. ER equals EPR is still a conjecture. Tensor networks give toy worlds, not ours. Add SCFT is rigorous, but our cosmos is add S. The lesson that travels is modest and useful. Geometry and cause look like summaries of deeper informational structure. When experiments spit out correlations that resist classical scripts, they might be sampling the pre-geometric rules those summaries rest on. Impact shows up in two places. First, it reframes no signaling stubbornness. Emergent geometry can bend in code space while still arranging itself so operational cause and effect respects light cones in the lab. Build enough entanglement and you get a smooth stage where signals behave. Slice it oddly and distance shrinks in correlation space, not in meters. Second, it explains why causal structure might flex. If order is a wiring property, not a global clock, then superposing orders is just superposing wirings. The switch stops being rebellious. It's a local override that routes influence through algorithms. Meanwhile, a 2018 calibration footnote started to glow. Back then, shifting the coincidence window W by 200 picoseconds slid a fringe phase exactly as the joint arrival model predicted. It felt like a nuisance. Under the emergent geometry lens, it read like a rule. The slice you choose is part of the geometry you infer. Move the slice, and you change which joint amplitudes are neighbors allowed to interfere. The lab's joke, phase by slice, not by signal, landed as a principle. Context picks pathways in code space. Chosen pathways define the effective geometry. A human beat kept the dream grounded. Anna's father listened to a late talk and said, "So space is feelings between things." Anna grinned. "Not feelings, relationships priced by entropy." He sighed in relief at the word entropy. Elena added, "What we call near is can exchange information cheaply. What we call before is many stories agree on the order." He nodded. "Most stories agree most of the time. The rest is where you design." That last line set their next task. If slices, windows, and bases are part of the geometry, then there's a deeper constraint hiding under the retro tug. Not no messages to the past. They already respected that, but you can't pick context for free. Try to torque one connection and the tension shows up somewhere else in the stats. Call it consistency of conditioning. It sounded like an accounting rule the network enforces. Elena tapped the old 2018 law. Let's reopen it. If the slice is part of the law, we should be able to name the law. The 2018 detail that won't go away. They hauled the old archive drive onto the bench and scrolled to spring 2018, the eraser run with the long fiber idlers. Stakes were higher than nostalgia. If a tiny calibration quirk shaped the retro feel, then maybe the feel wasn't fragility at all. Maybe it was a rule peeking through. Action started with the console and a boring parameter. The coincidence window W back then, they'd set W equals 2.5 nanoseconds. Detector jitter sat around 450 picoseconds. Fiber dispersion and clock drift stayed under a nanosecond across an hour. With that window, the erase basis gave clean fringes in coincidences. The which path basis gave flat sub-ensembles. They published, packed the rig, and moved on. What nobody tracked carefully was how sensitive visibility was to W. Fayez found a midnight note from a visiting student. Try W equals 3.5 ns. Fringe visibility drops tilde 8%. They de-shrugged it off as background. Marta replotted visibility versus window width across the whole week. The curve wasn't noise. It rose from too tight, peaked at a sweet spot, then fell smoothly as W widened and mismatched pairs crept in. Slide W left or right, and phase shifted with it. Stakes sharpened. If the pattern you care about swings with W, then the window isn't a neutral lens. It's part of the measurement. Choose it too wide and you average in accidental pairings that wash out interference. Choose it too narrow and you bias the sample, chopping real pairs and distorting the phase. Either way, the universe is telling you something simple and annoying. You can't pick context for free. Meanwhile, Elena pushed for a model, not a vibe. They measured detector response functions, fiber dispersion, and clock sync jitter. Then they built a synthetic joint arrival distribution PTS-T basis. They swept W across that distribution and computed the predicted conditional visibility VW. The simulation hugged the archival curve, peak and tails included. No mystery forces, no messages from the future. Just this, the coincidence window defines which joint amplitudes you let interfere. Move the window, move the interference. A micro story made it stick. Anna kept W fixed in width and slid its center by 200 picoseconds. The signal's conditional fringe walked in phase by exactly what the model said it should. She laughed. Phase by slice, not by signal. Her father glanced up from the printout. Like shifting the chorus against the drums. She nodded. Same tracks, new groove. Clarify what changed and what didn't. The raw signal counts on the screen never sprouted fringes after path marking. Those logs stayed logs. The late choice of the idler basis and the placement of W picked out sub-ensembles where joint amplitudes interfered constructively or destructively. That's post-selection and alignment, not retro-editing. No local marginal changed in response to a later knob. The no signaling checks still passed when they swept bases and windows. The retro tug was the feeling you get when the answer to a question only appears once you define the question precisely. Meanwhile, theory handed them a label they could live with: consistency of conditioning. In classical probability, conditioning on a later event updates beliefs about earlier variables without implying backwards influence. In quantum settings, measurements help define the properties you're asking about, and post-selection picks subspaces where interference lives. The coincidence window is part of the effective POVM on the joint system. Change it, and you've changed the measurement, not the past. A second micro story because the lab's honesty rode on it. Fayez widened W far beyond the sweet spot. The fringes collapsed into a shallow ripple. He winced. Feels like the past blurred because we got lazy. Elena said, the past didn't blur, our question did. He tightened W to the model's optimum. Visibility snapped back. In the log he wrote, statistics reward specificity. Impact reached beyond one rig. That 2018 curve became a litmus test. If a claimed retro effect morphed under benign changes to conditioning in ways a joint model predicts, it wasn't a message from tomorrow. It was context doing its lawful work. If it persisted across well-characterized window shifts, basis rotations, and drift, then it earned a harder look, maybe a time-symmetric constraint or a deeper structure in the process. Meanwhile, the emergent geometry hunch found a foothold. Under that lens, W didn't just gate coincidences. It chose which joint time bins were neighbors in correlation space allowed to interfere. Slide W and you rewired who meets whom in code space. The phase walk under a 200 picosecond shift stopped being a nuisance and started reading like a metric. You moved the cut, so the path through the network changed. No paradox needed. Human moment because language keeps people sane. Anna's father pointed at two plots, unsorted noise and sorted fringes, and asked, which one is real? Marta said, both. One's the whole ledger. One's the ledger filtered by the rule we declared. He nodded slowly. Courts do this. Same evidence, different charge. Elena capped the page with 3 lines in thick pen. 1. The slice is part of the instrument. 2. No signaling is non-negotiable. Check local marginals whenever you move a late knob. 3. Freedom isn't free. Every conditioning choice has a statistical price you must model and report. What nobody knew that spring was how often they'd reuse that checklist. It would rescue them from press-release traps, anchor new protocols where order is a resource, and set the stage for testing time-symmetric accounts without mistaking calibration for causation. The 2018 detail wasn't a footnote. It was a rule in disguise. Retrocausality without paradoxes. Elena opened a fresh notebook and wrote 3 names across the top: Price, Wharton, Aharonov. The stakes were clear enough to make the room go quiet. Could they keep strict locality at the explanatory level? No superluminal pushes across space. By letting the underlying variables depend on both the preparation and the later measurement context, and still never allow messages to yesterday. If that answer was yes, the retro tug they kept feeling would stop looking like a violation and start reading as a constraint. She sketched the map. Hugh Price's line: the time asymmetry we smuggle into explanations isn't in the microscopic laws, it's in the boundary conditions and the way we tell stories. Drop the habit that hidden variables are fixed only in the past, and the ontic state lambda can depend on earlier preparations and later settings. Ken Wharton took that move and wrapped it in a classical field picture over spacetime. Experiments become boundary value problems. Fix conditions at the initial and final surfaces. The interior adjusts to satisfy both. No signal races backward. There's just one consistent solution spanning the whole region. Meanwhile, the two-state vector formalism kept the math tight. Aharonov's team bookended quantum processes with a forward-evolving state from the past and a backward-evolving state from the post-selection. Weak measurements in the middle pick up weak values that depend on both. It reads retrocausal, but the guardrail holds. Earlier local marginals don't budge when you change later settings. You can't use the future to toggle what yesterday's local observer already recorded. Constraint, not control. Fayez translated it into a toy bell box on the whiteboard. Let lambda at the source depend on both settings, and B choose a distribution rho, lambda a B, and local response functions A lambda B, B lambda that reproduce the quantum CHSH correlations while keeping the local marginals flat. He coded a sample model. It hit the quantum bound and kept no signaling intact. He stared at the plot and said, "It feels like cheating." Elena shook her head. "It's a bill. We're paying with measurement independence at the microscopic level to keep locality in the deeper story. Operational freedom stays. Nobody can exploit lambda." Anna wrote costs in the margin and underlined it. Retrocausal accounts relax the assumption that settings are statistically independent of the ontic state, not as a lab conspiracy, but as a structural dependence in the model space. At macro scales, you still generate unpredictable settings with high min entropy. At the level where lambda lives, the joint constraints bind. Superdeterminism is the cartoon version where everything is pre-written. Retrocausality aims narrower. Preserve no signaling and practical freedom while letting the ontology span both ends in time. Skeptics push them toward tests. If retrocausal models need fine-tuning to keep no signaling exact, maybe structured loss or sequential weak measurements could pry a gap open. Marta designed a protocol with 2 weak probes between pre- and post-selection, and a tunable, basis-dependent loss in the final device. In simulations, standard quantum predictions held. A toy retrocausal model matched them unless the loss had a specific asymmetry, at which point it needed delicately balanced cancellations. She circled robustness and wrote, "Loss as lever." Elena insisted on the operational guardrails. Whatever picture they liked, 3 checks were non-negotiable. 1. Local marginals stay invariant when you sweep the late setting. No signaling audits plotted next to every effect size. 2. Conditioning is part of the instrument. Coincidence windows, post-selection rules, and drift models published and pre-registered. 3. Any retrocausal claim that saves locality must demonstrate that the dependence of lambda on settings can't be harvested to gain a device-independent advantage. or to leak information backward. Anna's father wandered in for coffee and caught the summary. "Are you saying tomorrow reaches back?" She grinned. "I'm saying our deeper map has two anchors, yesterday's prep and tomorrow's choice, and the road between them is fixed by both. You still can't send a postcard to your younger self." He nodded. "Like a guitar string fixed at both ends. Move either peg, the whole shape changes." Elena added, "And you don't strum Morse code into the past." Price's appetite for symmetry gave them language. Wharton's boundary fields gave them a picture. Aharonov's two-state vector gave them calculations. The payoffs were concrete in the lab's daily life. Retrocausal framing let them talk about delayed choice without anthropomorphizing photons. It forced them to treat post-selection hardware as part of the apparatus, not a statistical afterthought. It made "freedom isn't free" more than a slogan, an accounting rule. Every context you pick has a price in correlations, and that price shows up in the statistics you're allowed to see. Fayez wrote a final note on the whiteboard. "Constraint not equal to control," Marta added. "Locality kept, independence paid." Elena drew a box around both and said, "Now we try to bite it." They draft an experiment that varied post-selection loss structures, audited no signaling side by side with any effect, and tested whether a retrocausal model could match without delicate cancellation. If it could, the tug would have a clean, symmetric home. If it couldn't, the failure mode might be where the next principle lived. Either way, no messages to yesterday, and no wiggle room for wishful thinking. Realism on trial. What's real if outcomes aren't? By Friday coffee, the room had one question left on the board. If outcomes don't pre-exist the questions we ask, what's real enough to stand on? Stakes were personal and technical. If properties aren't waiting fully formed, you need a new anchor, something sturdier than vibes, to build instruments and tell truths that survive scrutiny. Elena started with the theorem that refuses to look away, Koch-Specker. In dimensions 3 and up, you can't assign pre-existing, non-contextual values to all observables so that each measurement just reads off what was already there. Non-contextual means the value of an observable shouldn't depend on which other compatible measurements ride along. Try to paint value assignments across the whole space, and the constraints tie themselves in knots. Labs have hammered this with contextuality inequalities on trapped ions, photons, and superconducting circuits. Violations appear where the theorem says they will. The apparatus matters, formally, not as an excuse, but as a rule. Meanwhile, a different blade, PBR, cut through a cherished escape hatch. For years, people hoped the wave function was just knowledge, a neat summary of ignorance about deeper states. Pusey, Barrett, and Rudolph wrote down an assumption: preparation independence. If you build two systems independently, their underlying states don't secretly correlate, and proved that, under that assumption, distinct pure quantum states can't share the same ontic description. If you buy the premise, the quantum state is psi-ontic, part of what's out there, not just a belief in your head. You can retreat by dropping preparation independence and allowing coordinated underlying states, but that's a bill with its own interest payments. And more recent work showed another crack for psi-epistemic dreams. In d greater or equal to 3, known psi-epistemic models can't represent state update under measurement correctly. State update isn't just belief revision. It has to match how instruments couple in sequences. Most toy models stumble there. A micro story nailed the pivot. A visiting researcher pitched his favorite psi-epistemic qubit model over lunch, distinct states overlapping on the same hidden variables, knowledge like all the way. Marta drew a simple sequential protocol: prepare, measure, update, measure again. His model produced the right single-shot stats but mangled the updated distribution, predicting outcomes that didn't show up in real optics. To patch it, he had to shrink the overlaps until they vanished. He stared, then sighed, so the state is in the world. He didn't love it, he stopped fighting it. Elena didn't gloat, she sorted the furniture. 1. The quantum state behaves like something real under clean assumptions. 2. Outcomes are contextual, the instrument code defines their meaning. 3. Correlations are primary, the facts we agree on live in structures across systems and often across time. With that, realism doesn't die, it mutates. It stops promising properties without a question and starts promising stable rules about how questions carve facts. Anna's father pointed at the chalked psi and asked, "Real like this table?" Elena shook her head. "Real like a field. You don't hold it, but it leaves tracks. Treat it as only knowledge and you mispredict what happens when we ask in sequence." He tapped the wood. "So a state we can't see directly, and relationships we better not ignore." Marta added, "And the relationships bite when you pretend they aren't part of the question." Meanwhile, contextuality, once a headache, became a resource. Resource theories treat contextuality the way they treat entanglement, as fuel for certain advantages. Circuits whose statistics can't be simulated by any non-contextual model line up suspiciously well with tasks where classical emulators sweat. In the lab, that wasn't philosophy. It was a compiler flag. Mark where contextuality witnesses light up, and you found zones where quantum routines earn their keep. A micro story flipped a skeptic. The same visitor came back months later with a contextuality-based randomness extractor. He debuilt a protocol where the amount of certified randomness followed from the strength of a contextuality witness, robust against specific losses. He slid the plot across the bench. "I came to bury realism. I'm leaving with a different one." Elena grinned. "Welcome. The ground's firmer when you stop asking it to be simple." What about hidden variable holdouts? Pilot wave accounts keep realism by letting guidance be non-local in space. Retrocausal accounts keep locality by letting the ontology depend on both ends in time. Objective collapse theories add dynamics that pick outcomes. Many worlds says psi never collapses and branches instead. The lab's discipline cut through spin. Whichever story you pick, it must respect no signaling, match sequential statistics, and survive calibration audits, windows, losses, drifts, without leaning on conspiracies. Within those guardrails, multiple ontologies can still ride the same math. Outside them, they crash into the same theorems. Elena wrote 3 lines in thick marker. Psi real under clean assumptions. Outcomes contextual. Correlations primary. Then she added a 4th, softer line. Records and redundancy make it livable. That last one mattered because the next questions would step back into kitchens and courtrooms, where our one-way lives hold us together, and ask how far quantum cracks extend before the arrow hardens and refuses to bend. Human time versus quantum time. By Monday, the whiteboard had 2 clocks sketched on it, one labeled human, one labeled quantum. The stakes were ordinary and huge. If quantum time bends around slices and boundary conditions, why does your day run straight? Why do blame, memory, and plans make sense at all? Start with the machinery that stiffens stories. A single qubit can carry superposed paths and let a late slice decide which pattern you'll see. A coffee mug can't. Decoherence sprays fragile phase information into a sea of degrees of freedom. Air molecules, desk vibrations, stray photons, so fast you can't gather it back. The quantum state doesn't collapse by proclamation. Coherence leaks into places you don't control and won't retrieve. That spray writes records, scratches, heat, photons bouncing off surfaces, synapses that rewait. Once those copies exist, interference between big, distinct histories becomes practically unreachable. The world goes from could be both to choose one and stick with it, because the environment chose for you. Meanwhile, entropy does its own blunt writing. Our universe carries a low entropy past. Typical evolutions fan out into more accessible microstates. That's the thermodynamic arrow. Yesterday left many traces. Tomorrow hasn't been redundantly etched yet. So remembering feels easy in one direction and impossible in the other. That asymmetry isn't a new law. It's the statistical weight of states that look time-directed when you average over what you can't track. Now thread that back through Elena's bench without repeating ourselves. The eraser's retro tug needed tight coincidence windows and post-selection to reveal conditional fringes. In a kitchen, you don't get to choose narrow slices after the fact. Your senses integrate broadly. Your appliances leak heat. Your decisions write to media that don't preserve phase. That averaging is mercy. It keeps daily causality intact. It's also why agency survives intact. Coarse variables obey dynamics where today screens off most of yesterday when you predict tomorrow. Planning works because the world, as you touch it, is nearly Markovian at the scales you operate. A micro-story kept it grounded. Anna's father burned his toast again. He tapped the toaster and said, "No post-selection to fix breakfast." Anna smiled. "There is one, set a timer next time." He laughed. "So I'm just choosing better slices." Elena called from the hallway. "You're choosing interventions that produce durable records in your favor." He nodded and reached for a plate. Quantum Darwinism tied that instinct to a rule. Environments don't just decohere. They redundantly broadcast certain stable facts, pointer states, so multiple observers can sample them without disturbance. That redundancy explains objectivity in daily life. Many cameras, many eyes, one table. The moon's position is there because photons have carried that information to every open sensor in sight. Nobody needs an interferometer to agree. The environment already did the work. The lab leaned into that divide. When they wanted indefinite order to pay, they fought redundancy. Isolate paths, match losses, keep the control qubit from leaking a who's first hint. When they wanted a sensor to hold spec through a rough week, they embraced redundancy. Error correct the classical side channels, average aggressively, build records that won't budge under drift. Same crew, two-time regimes. In one, meaning is global and conditional. In the other, meaning is local, recorded, and hard to move. Where do the cracks leak through? In mesoscopic islands where coherence outlasts noise long enough to matter. Superconducting circuits, cold atoms, defect spins in solids, even some biological complexes on picosecond scales. In those pockets, late conditioning and coherent order control are tools that change budgets. Outside them, HVAC cycles, streetlights, and footsteps smash coherence before you can ask quantum questions cleanly. Engineers live at that boundary. Citizens shouldn't have to. A human beat tested the ethics. After a public talk, someone asked if retrocausal framing meant forgiveness could be retroactive. Could a later change redeem an earlier harm? Elena exhaled. Physics gives constraints, not absolution. We can condition data late without rewriting records. That's why courts exist, to agree on which slices count and to keep those slices public. Anna's father added, and to decide which records we preserve. The team wrote a 4-line compass and taped it to the rack. 1. No signaling is non-negotiable. Always audit local marginals while you sweep any late knob. 2. Conditioning is part of the instrument. Report windows, filters, and losses and model how they shape the effective measurement. 3. Lean on thermodynamic arrows when designing human-scale systems. Redundancy is your friend. 4. Mark the boundary where the slice you pick changes what pattern means and label it for users. Impact folded back to their mission. They stopped selling time is broken and started teaching bilingualism. In human time, causes precede effects, records pile up and most stories agree. In quantum time, explanations live in correlations across the whole run, and some tasks let first be a knob you don't set. Both are true in their regimes. The trick is knowing which regime you're in. A last micro-story closed the loop. On Friday, Fayez printed 2 plots from the same dataset, unsorted noise and sorted fringes. He handed them to Anna's father. Which one is real? The older man asked himself aloud, then chuckled. Depends what we're asking. He pinned both to the corkboard, side by side, and wrote under them, 2 times 1 world. The room went quiet in the right way. They had their headline and their restraint in the same sentence. The crisis that reset the field. It started as a rumor about a sliding coincidence gate. Then plots disagreed. A preprint vanished, replaced by one with drift-tracked clocks, pre-registered windows, and blind analysis. Labs published raw-time tags, latency tables, RNG bias audits. Cosmic setting streams were rechecked. Spacetime diagrams got error bars. Fringes shrank, witnesses tightened, but violations survived. Checklists spread. Pre-register conditioning, separate exploration from confirmation, audit no signaling alongside effects. Hype cooled. Engineering won. the weirdness stayed smaller and harder to fake. What we can say for sure, and what we can't. By the time the checklists were taped to lab doors, Elena drew 2 columns on the board. Sure on the left, not yet on the right. Stakes were simple. If you want the public to trust the weirdness, you have to show where the floor is solid and where it's still scaffolding. Start where the ground doesn't give. Bell's verdict is secure. Loophole-free experiments, Delft with spins and entanglement swapping across kilometers, Boulder and Vienna with high efficiency, photon detectors and nanosecond switching, violated Bell inequalities under conditions designed by skeptics. Settings were generated fast, often with independent devices. Stations were space-like separated. All trials were counted with pre-registered analysis. And even when the tiny predictability of randomness was conservatively accounted for, the violations held with vanishing p-values. You can keep operational no signaling. You can't keep local realism. That means you can't have both pre-existing, measurement-independent properties and a local causal account that screens off distant events by their common past. One of those had to go. Experiments showed it's their conjunction that fails. Next rock. Indefinite causal order is real as an operational resource. Quantum switches implemented on photonic platforms, trapped ions, and NMR have passed causal witness tests that a mixture of fixed orders can't satisfy. Under reasonable assumptions, no superluminal influence between local labs and standard quantum operations inside each. Those witness values certify causal non-separability. Device-independent roots are emerging too. With extra structure and current assumptions, you can increasingly constrain or even rule out fixed order without trusting inner workings, in analogy to how Bell tests treat locality. This remains an active research area. None of this lets you send messages to the past. It does let you structure tasks so that who goes first never had a single answer, and then cache that structure in fewer queries or bits under matched noise. Third point on the rock side. Delayed choice and quantum eraser experiments behave exactly as the careful story says. Once path marking exists, the signal alone shows no interference in the raw counts. Condition on an idler measured in a complementary basis, and interference appears in sub-ensembles as predicted. Shift coincidence windows and phase and visibility track the joint arrival model. Too wide washes out pairs, too narrow chops real ones. Slide the window center and the conditional phase walks by the amount your jitter and dispersion predict. The retro feeling is emotional. The structure is conditional. No local marginal budges under later choices. No signaling checks pass when you sweep bases and windows. Fourth, contextuality is an operational constraint, not a vibe. Caution. Specker-style inequalities tailored to real hardware have been violated in ions, photons, and superconducting circuits. Outcome statistics can't be reproduced by any model that assigns non-contextual, pre-existing values to all observables. And under clean assumptions, especially preparation independence, the wave function behaves psi-ontically. PBR-type results show distinct pure states can't share an underlying ontic description. Retreats exist, but they cost you. Drop preparation independence, allow hidden correlations, or accept time-symmetric constraints on hidden variables. Add to that a practical blow to psi-epistemic models. In dimensions 3 and up, known epistemic models that dodge PBR fail to represent state update correctly under sequential measurements. The state isn't just knowledge if you want to get update right. Fifth, in the useful column, edges from indefinite order have moved from blackboard to bench. Query complexity separations exist for channel discrimination. Switch protocols can detect non-commutativity with fewer calls than any fixed order routine at the same error rate. Communication tasks show bit-level savings under matched noise. Metrology schemes under specific dephasing regimes see a lift in precision because interference between orders redistributes error. The gains are not universal, and they evaporate if you peek at the order mid-process or leak asymmetries that select a de facto order. Treat order coherence like entanglement. Protect it, certify it, spend it where the cost model says it pays. Now the not yet column, where words get careful. Retrocausal models remain frameworks, not settled physics. They offer a way to keep strict locality at the explanatory level by letting ontic states depend on both preparation and later settings, while preserving operational no signaling and practical freedom for experimenters. They fit known data when tuned, and they often require fine-tuning to keep no signaling exact in the presence of realistic loss and drift. Do they predict clean, testable deviations from standard quantum mechanics in achievable noise regimes? We don't have a consensus target. Proposals focus on sequential weak measurements with structured loss or on statistical signatures of too much fine-tuning, but the jury's still out. Also unsettled, spacetime as emergent beyond toy universes. ER equals EPR is a powerful conjecture linking entanglement to geometry. Tensor networks give clean models where distances reflect correlations, and AD-SCFT rigorously ties boundary entanglement to bulk areas and perturbatively to Einstein-like dynamics. Our universe isn't AD-S, and lab interferometers aren't holographic boundaries. The moral that travels: geometry and cause look like summaries of deeper informational structure, guides intuition, not a derivation for kitchens and cities. Turning that moral into lab-grade predictions is work in progress. Interpretations remain a marketplace where the math agrees and the metaphysics differs. Pilot Wave accounts by realism with non-local guidance. Many worlds buys determinism with branching. Objective collapse adds dynamics to pick outcomes. Time-symmetric and retrocausal approaches by locality with boundary condition dependence and reduced measurement independence at the ontic level. Experiments that separate these at scale are scarce because, in the regimes we can reach, they all reproduce the Born rule. Your bill comes in what you're willing to accept conceptually, and in the auxiliary assumptions you're willing to defend. Finally, the bridge to daily life is firm in practice and open in detail. Decoherence, redundancy, and entropy explain why our macroscopic arrow is strong, why records are durable, and why causality feels one way. Pockets of coherence in mesoscopic systems push quantum structure up the ladder. Superconductors, cold atoms defect spins, and there, late conditioning and order control can be tools. How far the cracks reach in complex, warm, wet systems is an empirical matter that biology and materials science are mapping carefully on fast timescales. The compass stays the same. Where coherence survives and conditioning is tight, quantum time pays. Where redundancy explodes, human time rules. Elena turned from the board and wrote a checklist under both columns: how to read the next headline without getting spun. 1. Find what was certified: entanglement, causal non-separability, contextuality, and look for the specific witnesses and their bounds. 2. Locate the conditioning, post-selection rules, coincidence windows, filters, and check whether the effect survives within a modeled, pre-registered range. 3. Verify no signaling audits, local marginals plotted against later choices. 4. Separate operations from interpretations. A causal witness violation isn't time travel. An eraser fringe isn't a message to the past. 5. When a theory promises to explain Bell locally, find the traded assumption, usually a softened measurement independence claim, and decide if that bill fits your palette. A student in the back asked Anna, "So is the universe causal or not?" Anna said, "Operationally, yes, in the slices we live by. Mathematically, causality can be conditional and sometimes optional in the regimes we engineer. Know which regime you're in." The room nodded, not because the weirdness shrank, but because the words got stricter. The story got tighter, and the promise, use the weirdness without lying about it, finally sounded like something people could build on. Causality didn't vanish. It narrowed to where records and redundancy lock stories, and loosened in the glass table regimes where coherence and conditioning define meaning across time. If you want the deeper cut on emergent spacetime and how entanglement might sketch gravity's blueprint, watch the next episode. Subscribe for more true lab stories where experiments, not metaphors, set the terms. And follow so you don't miss the moment the script slips again.